All right, my previous video went to the very, very max, so I'll try to make sure this one's a little bit quicker so I don't get cut off at the end. But we're going to look over carrying out significance tests or hypothesis tests for mu, a population mean. So remember, the symbols for population mean is a mu, and the sample mean is a x bar. So we'll be seeing both of these in all these problems. Something a little bit different with hypothesis tests for means than proportions is, just like with confidence intervals, if we know sigma, we're going to do a z-test, and we're going to use a normal distribution. If we don't know sigma, we're going to use a t-test, or we're going to do a t-test with a t-distribution. Remember, those t-distributions are based on degrees of freedom. So that'll come up again, just like I did with confidence intervals. So nothing, again, that's super, super new. And again, we're going to look at it in terms of a state plan do. And the state plan do is going to be the same here as it was for proportions. Only difference being we're talking about means for one. And then two, the conditions are slightly different. Remember, conditions for means are random and independent, or random and 10%. That's the same as proportions. But the normal condition for means depends on the sample size. And we'll see that here with an example or two. All right. Oh, here's this dissolved oxygen content again. The level of dissolved oxygen in a stream or river is an important indicator of the water's ability to support aquatic life. A researcher measures the DO level at 15 randomly chosen locations along a stream, and here are the results in milligrams per liter. A dissolved oxygen level below 5 milligrams puts aquatic life at risk. So things that are important here is 15 randomly chosen locations. My data is important. And then the last thing that's important here is this 5 milligrams per liter, because that's going to be what the population mean is known to be, or what we want the population mean to be. All right, so let's do our hypothesis test. We're going to do a state plan do. So just like with proportions in the state, we're going to give our significance level. If it's not given to us, we're going to pick our own. I usually pick 0.05, but there's several that are okay. And we're going to state our hypotheses, our null and alternative. And then we're also going to define our parameters. So in context, in this case, what does the mean? So let's look at the state plan do. So we're going to perform this test at the 0.05 level. Notice it wasn't given to us. That's my favorite sigma, or sorry, my favorite alpha level. So I always pick 0.05 if I have a choice. And then my null hypothesis is what the mean is known to be. So the mean dissolved oxygen level is known to be, or we want it to be, 5 or more. Okay, so a minimum here of 5. So my null hypothesis, the HO, mu has to equal 5. Then for the HA, anything below that is bad. So we want to know, well, is it below that? So our alternative is a less than. So mu less than 5. And then our parameter here, mu, is the true mean dissolved oxygen level of this stream. So here I'm defining my parameter. So 3 things. 1, significance level, check. 2, hypotheses, check. And 3, the parameter defined in context, check. Now the plan. Conditions here for a t-test. Why t-test? T-test because this is a sample and we don't know the population standard deviation. So we're going to have to use this sample standard deviation. So my conditions, just like confidence intervals, random, that's met because of the 15 randomly chosen locations. Independent, if you think about a stream, 15 locations in a stream is definitely less than 10% of the entire stream. And then third, normal, and I think this was on a previous quiz for confidence intervals. The normal condition here, 15 is less than 30, but T procedures are what we call robust, meaning they're a little bit resistant to that condition as long as there's no skew or outliers in the sample data. So luckily, because of I think it was the 8.3 homework quiz on confidence intervals, I still have this data in my calculator. And I checked this, I think in a video that I posted. If I look at a dot plot of the values, I don't see strong skew or outliers. It's tough to tell, so I think I made it into a box plot. You could do a histogram as well. So the box plot here isn't indicating any strong skew or outliers. So because T procedures are robust, I can go ahead and say the normal condition is met. So let's look here, the conditions in writing. So notice that they provided a picture. You don't have to provide a picture. You just have to say the data does not show strong skew or outliers. And then we also said the independent condition was met. Since our conditions are met, we can go on with the test. And there are two ways to do this. I kind of started here. If you consider the sampling distribution here, this is going to be a T distribution, not a normal distribution, so a T distribution. And unfortunately in the calculator, if I do a T-CDF, I need the T-score. I need this to be a T, not an X bar, meaning I need to make this to standard normal. And let me just show you how much work that is. So here, the formula for a T distribution is the value minus the mean. So here would be 4.77 minus the mean divided by the standard deviation. And here we calculated that was 0.243. So I need to calculate that value. And whatever I get there, it's some negative number. Then I can go to T-CDF, my degrees of freedom. And you could try this on your own. It's way more work than what I want to make you do. It takes too much time. But you could do a T-CDF with degrees of freedom equal to 14. And it'll spit out a probability. And it'll be the correct probability, but it's just a lot of work. So the other way you can go about this that's a little bit easier is using the calculator shortcut, similar for proportions. So if you go back to this page, I think I already did it. Nope, hold on. If you go to a calculator page and go to menu, statistics, stat test, this time we're going to pick a t-test. Just like with confidence intervals, if you wanted the cheat, you would pick a t-interval. My input method's data. The mean of the null is 5. The list I call DO. And I want a less than alternative. And I click OK. Let me just cut this out quick. So if you see here my results, I'm listed a p-value. I got the t-score. So I told you it would be some negative number, as you see. And if you were to do a T-CDF with that number, it would give you the same p-value. But what I care about is that p-value of 0.181. So 0.181 is the area in this red tail. So what does that tell us? Well, 0.181 is bigger. It's actually a lot bigger than the alpha level that I chose in the state. So 0.181 is bigger than 0.05. So in this case, my conclude, we're going to fail to reject because our p-value is greater than alpha. So let's go to the next page where that's listed, and there's that same p-value. So the p-value is greater than alpha of 0.05. You don't need that sentence about this first sentence. It's a little extra. But since our p-value is greater than 0.05, we fail to reject. We can't accept the null, but we don't have enough evidence to go against it. So that sample mean did not provide enough evidence to conclude that the mean oxygen level in the stream is less than 5. All right, here's another significance test for means. This one's going to be a two-sided test. This is the Hawaii Pineapple Company. They're interested in the sizes of the pineapples grown in the company's fields. Last year, the mean weight of the pineapples harvested in one large field was 31 ounces. A new irrigation system was installed in this field after the growing season. Managers wonder whether the change will affect the mean weight. To find out, they select and weigh a random sample of 50 pineapples. And they give us a computer output. Before I scroll to the computer output, they're looking for a change. So is it going to affect the mean? Will the change in irrigation affect the mean weight? So that's kind of shouting at us. It's going to be a two-tailed not equal to test. Let's look at this output of the computer. And notice it says determine if there are any outliers. That's going to be here in order to check the normal condition. Although our sample size was pretty big, so it's just good practice, I guess, to check for any outliers. So here is the sample size. There's the mean. Here's the standard error of the mean. So SE, remember, that's S over the square root of N. This standard deviation, or STDEV, that's just the standard deviation of the sample. And then here's my 5-number summary. So the IQR rule, given this information, is going to be Q1. I think it's written. I'm not going to bother wasting time writing it. Q1 minus 1.5 IQR and Q3 plus 1.5 IQR. There it is. What's going on with my hand here? So anything outside of those values is considered an outlier. And if you check it for this data, just to save a little time, for this data, if you do the Q3 plus 1.5 IQR, you get 40.3025. So if I look at my maximum, that's inside. So there's no outliers above the maximum. And then on the other side, if I do Q1 minus 1.5 IQR, I get 23.08. And I look at my minimum, that minimum is above it. So that means there's no outliers below it. So there's no outliers here. Even if there were, I wouldn't bother checking this on the AP exam because that sample size is big enough. So a sample of 50 pineapples is big enough. So we're going to go right into our hypothesis test. So for our hypothesis test, the null hypothesis is what the mean is known to be. And for us, that was the 31 ounces from the very beginning. This manager wants to know, is there a difference in the mean weight? So that means our alternative is going to be not equal to that 31. So there's mu equal to 31, mu not equal to 31. We have to explain what mu is. So here mu is the true the true mean of the pineapples in this large field. And alpha level, they didn't give us one. I picked 0.05 again. So my favorite alpha level to the rescue again. The plan, we're just going to check the same conditions. Random. They told us the pineapples were chosen at random up here. Normal, we kind of went over the normal. 50 is big enough here to say it's normal. And we also check for outliers. We're overachievers. We check for outliers. And then 10%, 50 pineapples. I'm not really sure how pineapples grow, but I'm guessing in a large field, that's less than 10% of all pineapples. So my conditions here are met. Let me cover my screen back up. So my conditions are all met. And then now I'm going to still do a one sample t-test, but this time I don't have the raw data. So let's see how that looks a little bit different. So I'm going to go menu statistics stat tests. We're doing a t-test. Again, t, because we don't know the population standard deviation. We don't have data. So last time I had raw data. I entered it in a list and spreadsheet. This time we have statistics. So I click OK. Here's my mean of my null is 31. The mean of the sample, let me go back. The mean of the sample was 31.935. 31.935. The standard deviation of the sample, notice not standard error, standard deviation. That's right here, 2.394. And the N was 50. And we're doing a two-tailed test. I'm going to leave that as not equal to. And here is my output. And wow, I see that p-value here is very small. I'm just going to go back to my screen and not copy and paste it. But I got a p-value of 0.008. Now 0.008, if I made that a percent, is 0.8%. That's very, very unlikely. So because that is so unlikely, our conclude. So here's my information, the same stuff from the test. On the exam, you would just write down everything that this calculator spits out. So on the exam, really your t-value, your p-value, df, x bar, s, and all of that, those things just list on your exam. And my conclusion, since the p-value is less than 0.05, you don't have to say this, it's less than our alpha level, we're going to reject the null. So we're going to reject the null hypothesis, and we're going to say the mean weight of pineapples is different from 31 ounces. And I'm going to post a third video. It's going to be short and sweet, but it's going to go into how confidence intervals and these stat tests relate and how they can kind of help each other, help us figure out, in this case, well, how did it change? Was it higher or was it lower?